Hello everyone. Here we continue with topic 5 for exam 3, which is case 3 for integrating powers of secants and tangents, and this one we're calling tangent all by itself, so integrating tangent alone. For tangent to the first, you might recall earlier in the semester we proved that the integral of tangent of u with respect to u is minus natural log absolute value of cosine of u. And so adopting the linear argument rule for that, the integral of tangent of kx with respect to x would be minus 1 over k natural log absolute value cosine of kx, and then plus or constant. So that's the way we handle tangent to the first. No need for a u substitution because it's a linear argument. So minus 1 over k is 7, natural log absolute value cosine, same argument, 7x, and then plus or constant. Now when we get to tangent squared, there's a little bit of an issue because in all of our previous cases, case 1 and case 2, we generated a derivative, or a derivative was there, either the secant squared or a secant tangent, and then we were able to use our little procedure to make u substitutions. But here, tangent squared is not the derivative of anything, so the only thing we could do is consider using our Pythagorean identity. So we have that 1 plus tangent squared theta is secant squared theta. So if we isolate tangent squared theta, that's secant squared theta minus 1. So we'll replace tangent squared of 6x by secant squared of 6x minus 1. And for simplicity, let's separate that into two integrals. Integral of secant squared of 6x with respect to x minus the integral of 1 with respect to x. And then notice that secant squared is integrable. That's actually one of our basic 6. The integral of secant squared of u is the tangent of u, because the derivative of tangent is secant squared, and we use the linear argument rule on that as well. So we get 1/6 tangent of 6x, and then minus integrating 1 with respect to x, we get x, and plus or constant. So then the question, what about a higher power, like tangent cubed? Well, in a sense, we're going to use the same procedure because secant squared can be generated from two factors of tangent, and that does represent the derivative of tangent. So we get the little cookbook recipe, isolated tangent squared, but then this is important. You're not going to save it because it's not the derivative of anything. What you're going to do is change it immediately to a secant squared of u minus 1 by the Pythagorean identity. And then, as I wrote here, distribute and continue, use previous methods as needed. In particular, it's going to be the method for an even power of secant, as we'll see. So, onto this example, tangent cubed. We'll take two factors away from tangent cubed. So that's tangent 2x. Those two factors of tangent that we borrowed over with the differential dx, but then change this immediately. So we've got the integral of tangent of 2x, and then tangent squared of 2x is secant squared of 2x minus 1. Okay, and then we'll distribute, separate it into two integrals. The integral of tangent 2x times secant squared of 2x with respect to x. And I'm going to go so far as to box out the secant squared of 2x dx at that point. And distributing minus the integral of tangent of 2x. The reason why I boxed off the secant squared is because it is the derivative of tangent. So that can represent the du. Do a u substitution right underneath this. U is tangent 2x. Du secant squared of 2x forget times 2. Differential dx as well, so modifying 1/2 du is secant squared of 2x dx. And we can make a u substitution. This tangent of 2x, you can consider it to the first power, so that'll be u to the first, and then the secant squared 2x dx makes up 1/2 du. So that change of variables gives us 1/2 integral u to the first with respect to u. And then let's not forget this integral here, the minus integral of tangent of 2x, which is readily integrable by the previous formula. So 1/2 tags along, u to the first integrates to be u squared over 2, minus, okay, now integrating tangent of 2x, linear argument rule, and our special formula, minus 1/2 natural log absolute value cosine of 2x, close up the absolute values, add our constant, and since there's only one u here, let's back substitute it, 1/4 tangent squared of 2x, and then plus 1/2 natural log absolute value cosine of 2x, and then plus our constant. Okay, so there's only 2 more examples left, and I think we'll try to finish them within this one video, so we won't have to have 2 parts this time. I'm trying to keep the videos under 15 minutes or so, because otherwise downloading becomes a little bit of an issue. Okay, same procedure. Okay, it's all tangent alone. Just take 2 factors away. So you got tangent squared 5x. Those 2 factors that we borrowed, push over with the differential dx. Don't box them off. Change them immediately. And so, by the Pythagorean identity, once again, I'll recopy the tangent squared of 5x, but then tangent squared of 5x can be changed to secant squared of 5x minus 1. Okay, then we'll distribute, separate it into 2 integrals, get the integral of tangent squared of 5x, and then secant squared of 5x dx. And notice once again, we'll box that off because that's the derivative of tangent. So it's a nice simple u substitution just like the last one. And then minus the integral of tangent squared of 5x. So it looks like here we'll have to use the identity again. Going to change that. Because that's exactly like the previous question we had. And here it looks like a u substitution. So show it right underneath. U is tangent of 5x du secant squared 5x. Don't forget times 5. Differential dx as well. So 1/5 du is secant squared 5x dx. Alright, change of variables. Oops, let's show it. This is u squared. And 1/5 du is the secant squared 5x dx. Okay, so change of variables now. 1/5 integral u squared with respect to u. Minus integral, as we said here, we'll change this to secant squared of 5x minus 1 again. And let's just jump right in and integrate. 1/5 u squared integrates to be u cubed over 3. Okay, integrating term by term here. Secant squared integrates to be tangent. Linear argument, so 1/5. Tangent 5x. Double negative makes positive. Integrating 1. With respect to x, we get x. So again, since there's only one u, let's back substitute. So 1/15 tangent cubed 5x and recopy the rest of this. Okay, so final example, tangent to the fifth of 3x. So, same procedure. What happens is, as you're going to notice here, if you haven't noticed already, once we apply the formula, it basically depresses the power of tangent. Because if we take two factors away again, in this case we're left with tangent cubed 3x, tangent squared 3x. And then we're going to change these, once again, by the identity. So that becomes secant squared of 3x minus 1 with respect to x. And once we distribute and separate into two integrals, we get tangent cubed 3x, secant squared 3x with respect to x, which again is going to be the du, and then minus the integral of tangent cubed of 3x. So this is what I was talking about in terms of like the power on tangent was depressed. And so I'm going to save all the integrations for later, because this tangent cubed now is like the problem on the previous page. That has to apply the method once again. So I'm going to save this integral. You don't have to really recopy it, but I'm going to. And then here, we're going to borrow two factors of tangent again, so it's the same method. And not going to box them off or anything, we're going to change them. Okay, a little tedious to recopy this over and over again, but for some reason I have a feeling I have enough time to do so. Okay, and then here we're going to change the tangent squared of 3x to secant squared 3x minus 1 again. And recopy. And now distribute and continue. So negative integral, once again the secant squared is going to be the du. And then we have positive, because the double negatives there, integral of tangent of 3x. Okay, so this tangent of 3x is readily integrable with respect to our special formula. And for these first two integrals, same u substitution. Pick u to be tangent 3x, du secant squared 3x dx. Oops, forgot the 3. So times 3 differential dx. So 1/3 du secant squared 3x dx. Okay, so now for these integrals, this represents u cubed, secant squared 3x dx, 1/3 du. Here's u to the first, and 1/3 du. And then the final integral is just fitting the form for the integral of tangent of kx, as we had done before. So change of variables, 1/3 integral u cubed with respect to u, minus 1/3 integral u to the first with respect to u, and recopy integral tangent of 3x with respect to x. Now we can integrate, so 1/3 u to the third integrates to be u to the fourth over 4. Next term, minus 1/3 e to the first, integrates to be u squared over 2. And then here we have plus tangent, integrates to be negative natural log absolute value of cosine, but because the argument 3x modified by 1/3. And so finally, I guess I'll put back my u's. You could write a little note if you want, but easy enough. So 1/12 tangent to the fourth of 3x is 1/6 tangent squared of 3x, and finally minus 1/3 natural log absolute value cosine 3x, and then plus or constant. Okay, so that's the end for this lesson. Just one more case left for secants and tangents, and then we'll move on to another integration technique.